That's what creates the.
I always have to brag in these sessions. Well, I've got 3 screens too.
Not that it's making things easier. That's what I meant. Okay, let's see if we can do something different here today. Share. Does this work?
Nope, still your presentation mode, not the presentation itself.
My goodness. Okay. Well,
you didn't stop sharing, by the way, in case you thought you were.
Okay.
I think you can go up to display settings in the upper left, and I think there's an option under there to just show one view.
Yep, I see it. I'm checking. Swap, percent view, and slideshow.
Hey, that's
there we go.
Hey,
that works.
Cool. Well, thanks a lot for that one. I've learned something new.
Yeah. Yep. Thank you, Michael. Appreciate that.
Right. So, Jessica, you want to kick it off?
Are we at time?
It's 5:15, so I think we should be good. Michael?
Yep. Please go ahead and start, Jessica. Thank you so much.
Okay, awesome. So, hi, everyone. I'm here today to talk about the white paper that the Immersion workstream has been working on for quite some time now. It's in regards to design guidelines for immersion-cooled IT equipment. And it's the authors of this is myself, Jessica Goldbrand from Intel, and the other authors are Jamil from 3M, Leonard from 2CRSI, Nigel from Vertiv, Rick from Flex, and Rolf from Asperitas. We've also had several reviewers of this document, and it's Alex and Larry from Green Revolution Cooling, Herb from Liquid Cool Solutions, and Rob from Dell. So this paper, it's already been mentioned a few times today, and this paper was aimed at, or is aimed at, talking really about what are the design guidelines for immersion going forward. There are some things that are, of course, are similarities with air cooling, but there are also other things that are very different. And those are the ones that we want to highlight in this document. And specifically, the design considerations that we are talking about in this document are what I'm showing here on the agenda. It's the material compatibility, it's the thermal design, mechanical design, software, and electrical considerations. So those are the different things that I'm going to mention here, go through at the really high level. And I should say also that this document is almost wrapped up and is expected to go in and be presented to the incubation committee next month. So hopefully this will be approved and accepted fairly soon. So if we're jumping in here to the material compatibility, it's really, that's as already again been mentioned today, it's really the foundation of everything when it comes to immersion or any type of liquid cooling in general. You need to make sure that the immersion fluid are compatible with the different components that go into the liquid. And therefore, it's also crucial that you understand and know what the wetted materials are that you're using in the immersion solution. You don't want to have any potential failures showing up because the liquids or the materials were not compatible with the liquid used. So it's also crucial to understand the mechanism between the immersion liquids and the components interaction to determine potential mitigation options. Just to mention one, for example, if the immersion liquid and the glue on labels are not compatible and labels start floating around in the tank, there might be different ways of solving that, of marking the boards or taking the labels off from the beginning. So there are, of course, mitigation options, but if you don't know what the mechanisms are, you don't really know what it is that you want to mitigate. So that's what that awareness is fundamental as well. And of course, you also need to make sure that the immersion liquid, the dielectric liquid, that the health of it is maintained during the lifespan of your installation, to make sure that you're tracking what the properties of the liquid is, to just make sure that there's not a lot of contaminants or other things going on with the liquid itself that changes the characteristics and potentially changes the capabilities of the solution. And there are different methodologies to use as well for testing for material compatibility. We divided here in the paper, or when we're talking in the immersion work group, we talk about the hydrocarbons, oils, are single phase, and general compatibility needs to be investigated there. So basically you can put materials into the liquid itself and, you know, potentially accelerate the temperature in order to see if you see any potential interaction between the liquid and the material under test. For the fluorochemicals, for single phase, here you're dealing instead with a secondary incompatibility. So the fluids are very inert. However, there are materials that can be leached out into the liquid, and these leached out materials can then be deposited in certain parts or interact with other materials in your immersion solution. So those are the secondary incompatibilities that you need to be aware of and look out for there. For two-phase immersion, so you're using fluorochemicals there, and you can use Soxhlet extraction, where you have the liquid being boiled off into gas. So you have clean and condensed again, so that you have clean fluid passing over the sample under test or the material under test, and then you're tracking what basically if there are any type of leaching out or chemical reaction between the liquids and the material under test there. So there are different methodologies, and these are all described in the white paper. Okay, so let's move on to second topic here with thermal design. So again, traditional used air cooling, we know how that works, but what is different than when we're dealing with immersion? So if we're starting off with single phase first, we can have either forced and or natural convection. And really forced flow is if you have a pump forcing the liquid or the fluid. And natural convection is that you have hot liquid is rising to the top and cold liquid is basically going to the bottom. These two, if you have forced, you also have natural convection in your solution. So making sure that they work together for the optimal solution is really preferred. You can enhance that convection or the cooling capability by either increasing the flow rate to generate more of a turbulent flow, or potentially unsteady. A turbulent flow you might not be able to get just due to the viscosity that you're dealing with in these liquids, and when you're comparing to traditionally used air cooling. And you can also maximize the flow through the heatsink. So that's of course what you would like to do in order to have as much heat transported away from the hot components, and provide the cold liquid to the hot components in the same way as we like to do, of course, in air cooling. For two-phase, there we're dealing with a slightly different phenomena. We're dealing with boiling, so we have the liquid to gas, the phase change of transporting and getting the heat away from the hot components. And then you have the condensation of gas to liquid on the top of the tank, if we're talking about tank installations here. And there you have then the condensation, and then the liquid is dripping back into the tank again. Here you're not necessarily having a heat sink, but you're using a different type, or if I call it a simplified heat sink, is really a surface, a boiling surface with nucleation sites. So you want to make sure that you're creating as many nucleation sites as possible in order to really get as optimal cooling capability as possible. And the trick here for two-phase is really of being able to re-wet the boiling surface. So as the bubble takes off, you want to make sure that the liquid has a quick entry into the boiling surface again, to make sure that you have that continuous heat transfer from the hot components. And in immersion, which is different than air cooling, right, is that the low power components may not require heat sinks here. So those could be removed. Okay, and if we're looking at the liquids themselves, so dealing with either hydrocarbon or fluorocarbons here, if we're looking at the specific heat between those and comparing that to air, that's what you see in the table here. You see hydrocarbon, fluorocarbon, and air in comparison in the first column. You have specific heat of those liquids, and then volume per kilograms in the third one. So we can see hydrocarbon is slightly lighter than water, for example. Fluorocarbon is slightly heavier. But if we're looking at really the energy that be able to be taken up by these liquids, if we're looking at joules per liter in the last column, we see that hydrocarbons and fluorocarbons are pretty similar, just looking at joules per liter for specific heat comparison. However, specific heat is not the only parameter that is important here when we're dealing with heat transfer, but it's really the flow rate. What type of flow rates will you be able to get in these liquids? And if we're starting off with single phase, looking at the heat sink design. So a lot of immersion, single phase immersion users today use an air heat sink design, which of course is not optimum or optimized for something that is a liquid that is much more viscous than air. So in order to design an optimized heat sink, you really need to know what the liquid and the flow characteristics are and how those parameters change over time and where you're operating, what the temperature range where you're operating is as well as then looking at the fin pitch, the fin specification, so really the width, the height, the thickness of the fins, as well as the heat sink base of how thick, how good is it at spreading heat, what type of heat source are you dealing with, how much do you need to spread it, is it more of a uniform heat source versus one that might have a lot of hot spots. And then you get to also component placement in the tank. And there are thermal shadowing effects for single phase, as was mentioned here earlier on as well. They are thermal shadowing effects similar to what's going on in air cooling. And when you're looking at placement of components, here again, we're considering a tank installation. And again, when you have a thermally stratified flow of cold liquid in the bottom and hot on top, or hotter on the top, you really want the high power components, or the components with the most stringent temperature requirements, to be in the bottom of the tank where you have the cold liquid, while the low power components or the components with not so stringent temperature requirements can then be in the top. So that's what design consideration, thermal design considerations for single phase. If we move on to two-phase, we're dealing with, I mentioned previously, of having boiling enhancement surfaces with nucleation sites on, or using boiling enhancement coating, or BEC, as we call it here. And the parameters that you can vary there are the coating thickness and the particle size, depending upon what liquid that is being used. And you can, the BEC base can either be potentially directly on the integrated heat spreader or on a copper plate, basically generating that BEC design and then putting the coating on top of it. When you're considering two-phase immersion and component placement in the tank, you're dealing with constant temperature in the tank because you're operating at the boiling temperature. And you're not really dealing with any thermal shadowing effects. Those are different, of course, design considerations than for single phase. So these are good to be aware of. When we're getting into the mechanical design, there are some considerations there, of course, as well. So if we're looking at the chassis itself, the dimension depends on tank size and the type of immersion. Yep. So what type of equipment that you want to put into the tank. There are no standard tank dimensions currently. Of course, you can get the tanks that are more of the standard 19-inch or 21-inch server size. However, there's not a standard depth of those tanks, and that's something that is at least good to be aware of, and it can be customized to what the customer wants. The chassis should allow for high density solution and of course fluid circulation, so allowing that fluid to go through the IT equipment that is inside of the chassis. There's also ergonomic considerations for installation and extraction. You should have handles or reinforced attachment points for lifts. So depending upon how heavy the IT equipment is that needs to be lifted up, you can use lifts for bigger or heavier solutions, while potentially some of them, but usually not preferred, that a person or two can lift them out of the tank. There should be also guiding features for installation and extraction to make it easier to get basically the IT equipment in and out of the tank, and making sure you're really not banging into any other surrounding IT equipment. There's also orientation of the components. So we talked about, for the thermal design considerations, that we want to make sure that we're not blocking the flow, and that how we can enhance the flow really going through the IT equipment for enhanced cooling capabilities. So we want to make sure that during installation, for example, heatsink fins is parallel to the thermal liquid flow, so you use if you're using forced convection together with natural convection, that they're working together. For cables and bus bars being used for power. So for cables, you got to ensure really that the cable length and that there's space available to be able to pull out the chassis if you need to get it out and service it. And upper side cables are highly recommended. So this again comes back to, if you're dealing with a tank installation, there's one side of the chassis that will be accessible, the top side, and that's where you would like to have all of your cables going in and out of. If you're dealing with bus bars, you can use the floating blind mate bus bar clip. And of course, it's recommended to have guiding features to be able to meet alignment tolerances, really when you're mating the chassis and the bus bar. So those are some of the considerations there. If we're looking at more of the power supply unit or if a power shelf is being used. There's different installation considerations there as well. It can either be installed near to the bottom of the tank for optimized cooling. This is true for, as we said, for single phase, if you're depending upon what the thermal requirements of those power supplies are. Or you can decide to install it in the upper part of the chassis for accessibility. So if it's something that the user or customer wants to be able to service often or be able to have easy access to, you want to place it, of course, in the upper part of the chassis. If you're using a power shelf, you want it to be easily accessible and be able to for being able to remove power modules in that power shelf, and being able to have them accessible from the top of the tank again. For bus bars, need to position those out of reach of the operators and be able to protect them from possible falling debris as well. So it's maybe a little slightly different considerations when it comes to immersion compared to again traditionally used air cooling. If we get into software considerations here, what is it that would be different for that? So from a thermal consideration, immersion is a more effective heat transfer medium, as we talked about here previously in this presentation, than air. So being able to adjust some temperature settings and to allow for higher temperature settings as well will be potentially beneficial when it comes here to be able to utilize all the benefits that are the really potential for immersion and be able to optimize those thermal protections. There's also, again, when comparing to air, since immersion is a more effective media in transporting the heat away, there's it might be opportunities here to be able to have the CPU operate in turbo mode for longer periods of time, just because you're able to create that more efficient cooling capability. And it can also then allow for potentially increased CPU performance as well. So those are some of the thermal considerations. If we're getting into system management, so in immersion, we don't need any fans, right? So if we're dealing with air-cooled boards, they will have fan and fan controls installed. We don't need those. If you're taking a board and redesigning it to go into immersion, you want to take those fans away or at least be able to disconnect them. Of course, you need still to have the IT equipment be functional, right? So there needs to be really capabilities to be able to detect that the fans have been removed and that the cooling is still there and provided, so you can still operate really your IT equipment. But there are also some opportunities for being able to report new type of parameters that are of importance when you start dunking IT equipment into immersion liquids. For example, the liquid temperatures, the flow rates, the liquid quality, tracking that over time, as mentioned before. If we're looking at the firmware for BIOS opportunities here, here's really the opportunities to be able to disable some of thermal protections. So many systems have thermal sensors to determine what the environmental temperatures are, if it's safe for the IT equipment to operate or switch on. And that some of those thermal limits can potentially be increased when dealing with immersion. So you want to make sure that they're basically, or the request here really from the focus group is to have the opportunity of being able to have something that is potentially air cooled and immersion, right? That there's something of a switch that you'll be able to flip that will allow those temperature limits to be slightly enhanced due to that you're dealing with a much more efficient cooling medium. So that's really of opportunities for the BIOS to be able to support both an air environment as well as an immersion environment. There's also opportunities for custom firmware to be released to vendors and integrators, and potential for custom SKUs here. So some of these considerations, for example, if you're taking a power supply and now you're dealing with maybe the fan has been removed or the fan is not operating, you still need to be able to operate that power supply in immersion, and cooling is being provided by the liquid, right? So those are some of the firmware opportunities there. Okay, so getting into the last chapter here of the electrical considerations. So for electrical considerations, the component placement can be optimized to reduce loss or improve latency. And here we're just highlighting as well that really any immersion IT equipment should include a detailed and robust test plan to ensure that the effects of immersion have been validated, right? And that's really talking about signal integrity. We now have a pretty good write-up in the document talking about the signal integrity testing and how to test it as well, to make sure that you're taking those considerations into account as well when choosing your immersion solution, as well as power consumption and loss. So summary, the immersion focus group has been working on a white paper that talks about design considerations for immersion cooled IT equipment. We've gone through, talked about at the very high level, of course, the material compatibility, thermal design, mechanical design, software, electrical considerations. And this white paper is being wrapped up and will be presented to the IC for acceptance, hopefully here in December. So hopefully we can come out and let everyone know in December that this has been approved and accepted by the incubation committee. The call to action is please join the immersion workstream and contribute. We meet each third Tuesday of the month. If you're interested in learning more, you have the documents on the wiki page. You can also join the mailing list. And if you have any questions, I would point you really to Rolf here, who is the immersion lead of the immersion sub project, and please get involved and participate and contribute. And for questions and answers, I would like to really call on all of the authors here, as well as the reviewers, to chime in as hopefully questions come in as well.
Hey, Jessica, thank you so much. We did have a question come in the chat while you were presenting. It was from
Okay.
He's asking, with two-phase, is departure from nucleate boiling DMB ever a concern?
Departure from nucleate boiling. Well, yeah, you need to be able, or you need to know where your operating range is, right? If you're dealing with nucleate boiling, or if you're dealing with pool boiling, or where you are really on the boiling curve, in order to know what type of cooling capability that you will get. And you need to make sure that you're designing really the BEC solution, so the boiling enhancement coated surface, for you to hopefully extend the the time that you're spending in that nucleation boiling phase as well. So yes, you need to be aware for two-phase cooling in what part of the regime that you're operating, and there's potential as well with the BEC design to extend the time that you're really spending in that region as well for your particular solution. But that's a design, certainly a design consideration as well. Thank you for bringing that up.
Of course. Thank you, Jessica. All right. Our next presenter, Mr. Rolf Brink, who we've already got here on the call.